say we are going to write the axis. Let's call this as x, this as z, and I'm going to draw the third axis, that is the y-axis. Now I'll be drawing a parallelepiped. Okay. So here we have a parallelepiped, and then if I want to represent the normal as well as shear stress on every given axis, the top face is going to have a normal stress of sigma z. You can see that the normal stress is going to be parallel with respect to the z axis, and then the shear stress, which is going to be parallel to x-axis, and another shear stress which is going to be parallel to your y-axis. Now the shear stress is going to be tau. With respect to z-axis we are writing, so z, and it is parallel to x, then tau z parallel to y. These are the forces that are going to be acting on the top surface of our parallelepiped. Now on the front surface of the parallelepiped, again we will be having three forces that are going to be acting. First, it's going to be this normal stress sigma y, and then a shear stress of tau yx, and then shear stress of tau yz. Next, I'm going to write for this particular phase the stresses. Okay, so first draw your arrow marks or stresses along parallel to your respective axis. This is obviously sigma x, then it is tau xy, and then tau xz. Alright. Next it is going to be with respect to the other faces, that is the bottom face, this side face, and then the behind face. I'm going to draw it using dotted lines for the behind faces. Okay. So we are going to have sigma y. I'm writing for the behind face now. This behind face. For the front face, it is tau y. For the front face, it is sigma y normal. So for the behind, it is going to be with respect to the opposite direction, sigma y. And then here we have written with respect to the upward direction as tau xy. Now it is opposite, tau yz, bottom direction. Next, we have written it along positive x-axis as tau yx. Now we are going to write it along negative y-axis as tau yx. It's very simple to remember. If on the top faces and front faces, we are going to write it along the positive directions, then just behind the faces, whichever we are going to take, we have to just write it with respect to the opposite directions, because they are going to cancel out each other. Next, coming to this face. Here, for this particular face, we have written it as sigma x in the positive direction. So, now it is going to be with respect to the negative direction, sigma x. We have written tau xz along the upward direction. It is going to be now along the downward direction, tau xz. Now, along the positive y-axis, we have written tau yx, tau xy. So, along the negative y-axis, I am going to write tau xy. Next, it is going to be the bottom face. Okay, so for this particular bottom face, on the top face, it was along positive z-axis, sigma z. So now it is downwards, sigma z. Along positive y, it was tau xy. Tau xy or tau zy are one and the same. So now along the negative axis I am going to write tau zy. Along positive x it was tau zx. Now along negative it's going to be tau zx. Okay. So here we have represented all the forces, 9 components of your stress at a point, that is your stress tensor, into a parallelepiped. Okay. Next we are going to start off with strain at a point. Now we spoke about what is stress. Coming to strain, the deformation that is going to occur as a result of the relative displacement between any given points in a body is called as strain. Say for example, I have a body like this. The length of your body, say it is L. Upon the application of force F, then my body will be deformed. This is the elongation that is occurring, and then say this is going to be delta L, and this entire thing is the new length, let us call it as L dash, that is going to be created. The deformation here is delta L. We have a positive deformation. All right, that is delta L. If there is elongation, it is positive. If there is compression, then it is going to be negative. I'll give you an example for negative deformation. Say I apply a force like this, and then if at all my body after the application of force becomes like this, then this is the negative deformation. Here we are talking about elongation, positive deformation, and then strain is nothing but delta L divided by L. Please remember, we will not be having any units for strain. Okay. If the size and shape of the body remains unchanged, then the deformation is known as a rigid body motion. I hope you remember. Say you have a body. Say we have 2 points A and B. Upon the application of forces, it can be any number of forces. Let us call this as F1, F2, F3, and then F4 forces. After the application of these forces, if the distance between these 2 points, that is called as L. Before the application of forces, if the distance between any 2 points in a given body is L, and after the application of forces, if the distance between these 2 points after the application of forces, okay, I'm talking about after the application of forces, if there is no deformation or if the distance between the 2 points remains the same, then we call this as a rigid body motion. Okay. This is a rigid body motion. The body is called as a rigid body. The motion is called as a rigid body motion. If the shape and size of a body are altered, that is, the distance between any 2 points of a given body changes, alters, it gets transformed from one configuration to another configuration, then we tell that there is a deformation that has occurred. The matter that is present in the neighborhood of each point is translated and rotated and thus strained. There is going to be differences with respect to the distance between any given points in a particular body. Okay, so that is your strain. So using the concepts of continuum, the displacement components are considered to be functions of coordinates, and these functions are the derivatives with respect to coordinates and are assumed to be continuous. So again we are going to have two different types of strain, that is normal strain and then shearing strain. So we are going to have a normal strain. So this is a normal strain. I can denote it using epsilon, and then a shearing strain. How we had in stress a normal stress and a shear stress. Similarly, we'll be having a normal strain as well as shearing strain. Shearing strain is represented by gamma. Alright. Now, the normal strain is defined as change in length of a small line segment divided by the length of the segment. Change in length of a small line segment, this is a change in length, divided by the total length is called as normal strain. The shearing strain is the change in angle between two initially perpendicular line segments. Alright, say we speak shear with respect to two edges. Yes, so these are initially perpendicular. This angle, if this angle changes after the application of forces, say it becomes something like this, the body which was like this, after the application of forces became like this or became like this, it can be in any way. Okay, so if the angle between the initially perpendicular line segments changes, then it is called as a shear strain. Similarly, how we had three components and three coordinate axes for stress, we have three components and then three coordinate axes for strain also. We have a strain tensor that is going to be generated. This strain tensor can be written in the form of a matrix as epsilon x gamma xy by 2 gamma xz by 2 gamma xy by 2 epsilon y and then gamma yz by 2 gamma xz by 2 gamma yz by 2 and then epsilon z. Or I can also rewrite my strain tensor as gamma epsilon x, epsilon xy, epsilon xz, epsilon xy, epsilon y, epsilon yz, epsilon xz, epsilon yz, and then epsilon z. You need to remember these two, because if in the problems they give you with respect to epsilon xz, then you have to use this. If they give you in terms of the shearing strain, that is gamma, then you need to remember this. Alright. Next we are going to start off with components of strain. The same way that we had written the components of stress, we have components of strain. The components of strain are nothing but the strain tensor that I had done right now. Here I am going to write the components of strain with strain displacement relation. Okay. Now here, first I'm going to write it in terms of Cartesian coordinate system. We have Cartesian as well as polar coordinate system. X, Y, Z are the Cartesian coordinate system. Let us start with X, Y, Z. So, for X, Y, Z coordinates, let us say the component of strain is going to be U for X, V for Y, and W for Z. Epsilon X, that is normal strain in X axis, is nothing but dou Ux by dou X, or you can just simply write it as dou U by dou X. Okay, and then epsilon Y is similarly dou V by dou Y. Epsilon Z is dou W by dou Z. Now, coming to the shearing strain, gamma xy. I'll call it as gamma xy by 2 so that I will have the other component, that is epsilon xy, as a whole number. So gamma xy by 2 is equal to epsilon xy is equal to half of, okay, you have x, you have y. So x is dou u, y is dou v. Here we have written it as u and v. We just have a small differentiating thing, that is, it is going to be dou u by dou y and not dou u by dou x plus dou v by dou x. You have x and y component. So x and y means it is dou u and dou v, just that the denominators are going to be opposite. Similarly, next is gamma yz divided by 2. That is nothing but epsilon yz is equal to half of, let us first write the numerators, dou y, that is v, dou z, that is nothing but w. Now the denominators, for y I am going to write z, for w I am going to write y. Okay, the last component is gamma xz by 2 or epsilon xz. First write the numerators. For x it is u, for z it is w. Next, the denominators x and z. So this is z and then this is x. So these are nothing but the strain displacement relationship. Okay, next. Let us talk about components of strain in terms of stress components. So we know about the stress tensor, we know about the strain tensor, we know about the strain displacement relationships. Now I'm going to combine stress and strain. So epsilon x is equal to 1 divided by E. E is nothing but the modulus of elasticity, that is your Young's modulus, of sigma x minus mu times sigma y plus sigma z. Mu is nothing but the Poisson's ratio. Poisson's ratio is going to vary for every single material. Then epsilon y is 1 divided by E into, please remember, it's a very easy way to remember. We have three components, x, y, and z. I'm writing for epsilon x, so 1 by E of epsilon x, so sigma x, minus Poisson's ratio times the other two components, that is y and z, so summation of them, sigma y plus sigma z. Now I'm going to write for y, epsilon y, so first it is going to be sigma y minus mu times summation of the other two components, that is nothing but x and then z. The last one is epsilon z is equal to 1 by E sigma z minus mu times the other two components are x and y, summation of these two. So here mu is nothing but the Poisson's ratio, and then E is nothing but modulus of elasticity. Okay.